Continuity is the first concept in which you are going to get to use your recently acquired knowledge about limits. Continuity is an important concept because we are going to use it in defining the derivative. It also appears in several important theorems that we will be learning. The following is what you need to know about continuity. First, you need to understand what it means verbally and intuitively and how that applies to the algebra of a function. You will also need to be able to prove if a function is continuous at a particular point and at an endpoint. You will also need to be able to determine if a function is continuous on a particular interval and be able to find an interval upon which it is continuous. This is part one of a three-part video on continuity. This part will examine what it means for a function or graph to be continuous, and more specifically, what it means to be continuous at a point. You can tell if a graph is continuous just by looking at it. Can it be drawn without lifting your pencil? If it can, then it's continuous. This is good information as you begin your investigation, but it's nothing that can really be used in a proof. In other words, you can't use drawn without lifting my pencil as proof that a function is continuous in your homework or on a test. I like the explanation that a continuous process is one that occurs gradually without interruption or abrupt change. Here is the graph of a stone being thrown in the air as a function of time. The y-axis represents the stone's heights in meters after t seconds from when it's thrown. Now notice that as the stone reaches its maximum height, it slows down gradually until it stops and then returns to the ground, slowly gaining speed as it goes. The stone passes through every height until it reaches its maximum height. Notice that it doesn't skip over any heights or abruptly jump between heights. These are characteristics of a continuous function. This next graph shows the parking fee in dollars given the number of hours in the lot. Notice that from 0 to 1 hours, the parking is free, and from 1 to 2 hours, the cost is $1. There is no time, however, that the cost is 50 cents. The cost jumps from being free to $1 and doesn't gradually increase up to $1. These are characteristics of a discontinuous function. Let's now talk about what it means specifically for a function to be continuous at a point. The theorem implies that in order for f of x to be continuous at x equals a, the following three things must occur. First, at a, the function f of x must be defined. Second, the two-sided limit as x approaches a must exist. Finally, third, the function's value at a must equal the limit's value. Let's look at a graph that will help you visualize these three parts to point continuity. First, notice that the function value is defined at x equals a. F of a is the height of the solid dot. Next, notice that both the left-hand limit and the right-hand limit are approaching the same height. In other words, the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right are equal. This implies that the two-sided limit exists. Finally, notice how the function's height at x equals a, that of f of a, is the same value as the limit as x approaches a. This proves that f of x is continuous at x equals a. Let's look at some examples of graphs that are not continuous. We will give a reason why they are not continuous using the three parts of point continuity, and we will name the type of discontinuity that exists. In our first graph, when x is equal to 2, the graph is not defined. We can stop right here. Our graph is not continuous. We call this a removable discontinuity because the discontinuity occurs at a little hole, and if we remove the hole, or I guess filled it, then it would become continuous. In this next example, at x equals 0, we can see that the function is defined. Y is equal to 1 when x is equal to 0. However, the two-sided limit as x approaches 0 does not exist. Both the right and the left-sided limits approach infinity. An infinite limit is really describing how the limit does not exist. We call this an infinite discontinuity. This graph is defined at x equals 2, and the limit as x approaches 2 from both sides also exists. Despite the fact that the limit exists and the function is defined, x equals 2 is still a point of discontinuity because the limit does not equal the function value for x equals 2. This is another removable discontinuity. In this last example, the graph is defined for x equals 3. However, the two-sided limit as x approaches 3 does not exist. This occurs because the limit as x approaches 3 from the left doesn't equal the limit as x approaches 3 from the right. Hence, the two-sided limit does not exist. This is known as a jump discontinuity.